Hello students, in this session we will talk about quality control charts and their applications. We draw quality control charts to observe two types of variables, qualitative or quantitative variables. Qualitative approach we apply when we categorize the items, for instance, as defective or non-defectives in a production process. Whereas in quantitative variable, we observe the quantities that are being filled, for instance, in a tube of toothpaste, as per the advertised quantity. So whether since the manufacturing process is going on using the machines, therefore there is always some chance of variation. Some sort of variation we expect because this is the natural processes. But sometimes or some of the variation is not allowed if it is repeated by the same cycle. For instance, in case of control charts, when we observe a qualitative variable, we go for P chart or chart for proportions. And in case of quantitative variable, we either go for range chart, chart for the mean, and chart for the standard deviation as well. But in our course outline, these three charts are included, so we'll be focusing on these three. Early on, I am talking about the three different types of variations that may occur in a process that we observe for the quality conformances. First type of variation is the random variation that is inevitable to occur because we cannot control the process perfectly, and there is always the situation where we observe variation in output as well as variation in the quality perspective as well. So both quantity and quality perspectives are affected usually, and this we call the random variation. Another type of variation that should not be there is the systematic variation. If something is occurring after a passage of time repeatedly with certain or constant frequency, then we can identify that particular type of variation as a systematic variation because it is always the system that is responsible for that particular type of variation, and the system in that case needs a correction, and if it is corrected for that variation or for that error, then we can control systematic variation in this way. Third type of variation is a special cause variation, and special cause variation occurs due to the factors that are beyond our control. For instance, some sort of natural disaster, a sudden or spontaneous incident that may occur that may disrupt the quality as well as quantity of the production process. For instance, strike in a factory that may occur randomly, and that definitely seizes or stops the production process, whether it is manufacturing or service providing. So these three types of variation are usually there in the data. Random variation we expect to occur in a process, but as far as systematic and special cause variation are concerned, it is not a good thing for the process that we are observing. Systematic variation can be controlled. Special cause variation cannot be controlled because it is beyond our control. It is due to natural disasters mainly. As far as control charts are concerned, so we focus on the mean value of the random variable that we are observing and their control limits. And control limits are either the lower control limit that gives us the lower bound for the process, and we denote it as LCL, that stands for lower control limit. Similarly, the upper bound for the control limit is considered as upper control limit. And how do we determine the lower control limit and the upper control limit values? We apply the 3 standard error times rule in that case. So if our variable is x that we are observing, then x plus minus 3 times standard deviation of x helps us to identify an outlier. If our variable changes to x bar, then this should be 3 times sigma of x bar. So this is how we apply or use to identify the outlier. Outlier in the perspective of quality control applications are the observations that lies outside the lower or upper control limit, and that shouldn't be there. So there are two types of variation that should not be there in the data, in the production process, or in the quality observance procedure. That is systematic and special cause. Now what we do, I am changing the page and I am going to draw the P chart. P chart is the chart for proportions, and proportions we go for when we observe a qualitative variable. Over here I am taking an example of a hotel in which there are 200 rooms, and hotel management or staff is responsible to check every day all, let's suppose, all 200 rooms on a daily basis, whether all the appliances or the items according to the quality standards are working fine, and that we call the conformances. If the appliances or the items are working according to the quality standard, then we call it conformances. If not, we call it non-conformances. So what we observe, let's suppose we have observed this phenomenon on 10 consecutive days. Day 1, day 2, day 3, day 4, day 5, day 6, day 7, day 8, day 9, and day 10. Then we have, let's suppose, number of rooms studied, observed, or checked as per the checklist predefined. So let's assume that this is the constant number of items or number of rooms that we have observed on a daily basis, and that's 200. Now I am giving you some random values. Let's suppose out of 200, the number of non-conformances here in this perspective, the number of rooms not ready to be occupied by the incoming guests. So let's assume that there are 12 rooms on day 1 we have found not ready, 15 on day 2, 18 on day 3, 13 on day 4, 14 on day 5, 15 on day 3, day 6, then 18 on day 7, then 10 on day 8, then 12 on day 9, and 16 on day 10. Now, how do we compute proportions of non-conformances each day? By just simply dividing the number of conformances each day by the number of rooms studied each day. So P we can compute as 0.06, then 0.075, then 0.09, then 0.065, then 0.07, then 0.075, then 0.09, 0.05, 0.06, and 0.08. Now, first of all, we are going to introduce the control limits, and for control limits we take help from the formula for proportion that we have used for CI. So this is how we have used the formula. Instead of taking z alpha by 2, take 3 times the standard error of sigma p hat. So what we did over there, standard error of random variable p hat we have estimated over there as p hat q hat divided by n inside the root. Over here our variable is p, so we make amendment in the formula accordingly, and that would give us p is our random variable. So a consensus value we can obtain from all the values of p, or a unique value as the mean of proportions. So p bar is our variable. So 3 times inside the square root, what we do, that's p bar multiplied by q bar and divided by n bar. So when we subtract from p bar this 3 times standard error factor, we get the lower control limit, and when we add to that p bar this standard error 3 times standard error factor, we get the upper control limit. So LCL has the formula p bar minus 3 times square root of p bar q bar on n bar, whereas UCL has the formula p bar plus 3 times square root of p bar q bar over n bar. Now we are going to compute p bar. This we can compute simply as taking the sum of all the values of p, 0.06 plus 0.075 plus 0.09 plus 0.065 plus 0.07 plus 0.075 plus 0.09 plus 0.05 plus 0.06 and plus 0.08. That's 0.715 is the sum. And 0.0715 would be the p bar value. P bar equals summation pi values divided by k. K represents the number of days or the number of values. That's 0.0715, and this we can round it off for 2 decimal places, 3 decimal places. as 0.072 for the sake of convenience of drawing or locating the values on the graph, because it is relatively difficult to spot or locate the value at the fourth decimal place. Now we are going to compute lower control limit and upper control limit as well. For this, better if we work out this factor that is to be added and subtracted to this one. Here n bar will be equal to summation n I values, the number of items we checked on every day, on each day, divided by the total number of days. So when we add them all, we get the sum of 2000 because this is the constant value. This may differ when on each day the number of rooms studied are varying. In that case, we add them all and then we divide by the number of observation, number of days. So 2000 divided by 10 gives us 200 as a p bar, as a n bar value. Now 3 times inside the square root 0.072. If p bar is 0.072, then q bar would be 1 minus 0.072, that would be 0.9, 2 and 8, and then divide by 200. Now what we do, you multiply 0.072 by 0.928 and then divide this by 200, and then we need to take a square root of this answer, 0.00033. That's 0.018, and then multiply this by 3. That gives us 0.0552. So we can again round it off to 3 decimal places. Now we determine LCL as 0.072 minus 0.055. That gives us 0.072 minus 0.055 is 0.017, and then UCL as 0.072 plus 0.055. And this is 0.127. Mean value is 0.072. So what we do, we draw the control chart now, and we have to scale this vertical axis according to the limits within which we are supposed to draw the control chart, either the limits or the minimum and the maximum value provided in the data. Minimum value is 0.0605. So we start our graph with 0.05 and we go up to the upper limit. Lower limit is 0.017, so we start our graph or scale as 0.01 and up to 0.12. So let's assume that this is 0.01, then 0.02, then we have 0.03, then 0.04, 0.05, 0.06, 0.07, 0.08, 0.09, 0.10, 0.1211, then 0.12, and then 0.13. That's all. Now we can ignore this part. Okay, we will draw the lower control limit at 0.017. That would be located over here, and we draw a dotted line to indicate the lower control limit. Now we go for the P bar line, that is at 0.072, and what we do, we draw the mean line as a solid line. That's P bar. Then 0.127, again as a dotted line. For UCL. Now we label the days or indicate the days on the horizontal axis. And we will start locating the values as per the days. So day 1 represents the value as is 0.06, then 0.075 somewhere over here for day 2, then for day 3 that's 0.09 approximately here, then day 4 0.065, it's gone down again and it is over here, located over here, then day 5 0.07, that's over here, then 0.075 here, then 0.075, 0.09 on day 7, then 0.05 here, 0.06 here, and 0.08 here. So we can observe that on none of the days the control chart is crossing neither the lower control limit and nor the upper control limit. Therefore, as far as special cause variation is concerned, the graph is not indicating any problem. Furthermore, we need to observe any existence of systematic variation in the data, and systematic variation we can spot by choosing a number as starting number and then observe that at least 2 observations are repeated after that starting number in the same order with the same value. So if we consider 0.075, so 0.075 is over here as well as over here. The sequence of values is after 0.075, that's 0.09, that matches over here as well. But if we consider the third value, that's 0.065, but over here it is 0.05. So the first two values, the starting and the second value is same, but the third value is different. Therefore, we cannot say that there is an existence of systematic variation in the data or in the control chart. So since this control chart neither contains any systematic variation nor special cause variation, Therefore, our conclusion for this chart would be the process is in statistical control. That's all for this.